Chapter 10, the CAD Kernel Revolution, From Drafting Tables to Digital Twins. The Geometry Engine. The fluorescent lights hummed overhead in General Motors' Warren Technical Center as Chuck Eastman hunched over his terminal in 1973, wrestling with what would become the most expensive software mistake in automotive history. His team was building Build, an early parametric modeling system that promised to revolutionize car design. The prototype worked too well. When word leaked that a single engineer could now do the work of 20 draftsmen, the UAW threatened to strike. GM quietly shelved Build, but the genie was out of the bottle. Across the Atlantic, a different revolution was brewing. Pierre Bézier, working in Renault's cramped engineering offices, was developing mathematical curves that could describe the flowing lines of French automotive design. His NURBS, non-uniform rational B-splines, weren't just mathematical abstractions, they were weapons in the coming war between American brute force computing and European mathematical elegance. The CAD Kernel Wars of the 1980s would make the browser wars look like a garden party. At stake wasn't just software supremacy, but control over how humanity would design everything from toasters to space shuttles. The evolution of CAD kernels mirrors the semiconductor industry's Moore's Law, but with a cruel twist. Each geometry breakthrough unlocked new engineering paradigms while simultaneously obsoleting entire classes of engineers. The kernel wars begin. By 1985, the battlefield was set. On one side stood Parasolid, created by Shape Data Limited in Cambridge, England. Their founder, Ian Braid, had cut his teeth on solid modeling at Cambridge University's computer lab, where punched cards and overnight batch processing taught programmers to think carefully before coding. Parasolid's boundary representation (BREP) approach was mathematically pure, every surface defined by its edges, every edge by its vertices, building solid models from the ground up with surgical precision. The challenger emerged from Spatial Technology Corporation in Boulder, Colorado, where American pragmatism met Silicon Valley venture capital. ASUS, Alan, Charles, Ian's system, named after its three British founders who'd fled Cambridge for Colorado gold, took a hybrid approach. Where Parasolid was a perfectionist's dream, ASUS was an engineer's compromise, mixing wireframes, surfaces, and solids in whatever combination got the job done fastest. The first shots were fired in Detroit's auto plants. Chrysler's engineers, desperate to catch Toyota's quality revolution, became the testing ground. A single fender design would consume 200 hours of modeling time in Parasolid's precise BREP system. ASUS could rough out the same fender in 40 hours, but with gaps and inconsistencies that would haunt downstream manufacturing. The choice became philosophical: mathematical purity or practical speed? The timeline of triumph and tragedy. 1963, the Genesis Ivan Sutherland sketchpad demonstration at MIT didn't just create interactive graphics, it created the dream of direct manipulation. For the first time, an engineer could sketch on a screen and watch the computer interpret their intent. The Lincoln Laboratory demo room fell silent as Sutherland drew a perfect circle with wobbly mouse movements, the constraint solver automatically correcting his human imperfection. 1985, the Parametric Revolution Pro/Engineers launch at the Boston Computer Society meeting changed everything. Sam Geisberg, the Israeli-born former computer vision refugee, stood before 300 skeptical engineers and demonstrated history-based parametric modeling. He drew a simple bracket, added dimensions, then modified a single parameter. The entire model rebuilt automatically, propagating changes through every feature. Half the audience dismissed it as a parlor trick. The other half recognized the future of engineering. The demonstration's real power wasn't in the software, it was in the philosophy. For the first time, design intent could be captured and preserved. An engineer's decisions became DNA, embedded in the model itself. When Boeing began using Pro/E for the 777 program, they discovered something unprecedented: components designed by teams in Seattle automatically fit with assemblies created in Wichita. The age of paperless aerospace had begun. 1999, the hybrid moment. Spatial Corporation's ASUS version 7 announcement at the SIGGRAPH conference barely registered in the trade press, but it represented a seismic shift. The new release seamlessly blended NURBS surfaces with polygon meshes, allowing designers to start with precise mathematical surfaces and automatically generate gaming engine-ready faceted models. Electronic Arts quietly began using ASIS-based tools to create Need for Speed car models that looked photorealistic in game engines while maintaining parametric editability. The implications rippled across industries. Industrial designers could now create organic forms in traditional CAD systems, bridging the gap between artistic vision and manufacturing reality. Apple's Jonathan Ive, struggling with the original IMAX translucent curves, found salvation in ASIS's hybrid approach. The same mathematical surface could drive both CNC toolpaths for injection molding and ray-traced renderings for marketing photography. 2010, the direct modeling resurrection. Autodesk's Inventor Fusion announcement at Autodesk University seemed like corporate desperation. Parametric modeling had won the CAD Wars, so why resurrect the supposedly dead direct modeling approach? The answer came from an unexpected source: repair shops and small manufacturers who couldn't afford the time or training for complex parametric systems. Fusion's push-pull interface let technicians modify imported models without understanding their parametric history. A cracked automotive part could be repaired by simply pushing surfaces until they looked right, then generating manufacturing data directly. Within 2 years, half of all automotive aftermarket parts were being designed in direct modeling systems, challenging the parametric orthodoxy that had dominated for decades. 2022, the Omniverse Gambit. NVIDIA's Omniverse CAD workflow announcement at GTC 2022 seemed like another graphics company overreaching into software. But the demonstration revealed something profound: real-time collaborative modeling across different CAD kernels. Engineers using Parasolid-based SolidWorks could work simultaneously with ASIS-based Inventor users, all changes synchronized in real-time through USD, Universal Scene Description, format. The demo showed a Formula One team designing aerodynamic components across 3 continents. The aerodynamicist in Woking modeled wing profiles in SolidWorks, while the stress analyst in Indianapolis ran FEA using the same geometry in ANSYS, and the manufacturing engineer in Milan generated toolpaths in Mastercam, all working on the same live model. The kernel wars weren't ending, they were evolving into kernel cooperation. Market forces shaping digital reality. The CAD kernel landscape became a mirror of global industrial power. German precision met American scalability in the battle for manufacturing supremacy. Automotive ascendant Siemens NX's synchronous technology deployment at BMW's Munich headquarters in 2008 represented more than a software upgrade, it was industrial philosophy made manifest. Traditional parametric modeling locked engineers into rigid design sequences. Change an early feature, and downstream dependencies could explode into geometric chaos. Synchronous technology broke these chains, allowing modifications at any stage without breaking the parametric chain. The results were immediate and dramatic. BMW's design change cycle, previously a 40-hour ordeal of model rebuilding and constraint fixing, dropped to 8 hours. More importantly, designers regained creative freedom. The E93 series facelift, completed entirely using synchronous workflows, reduced development time by 6 months while improving aerodynamic efficiency by 12%. Consumer Electronics Revolution PTC Creo's subdivision surface implementation seemed like academic indulgence until Apple's design team embraced it for the iPhone XS development. Traditional NURBS modeling excelled at mechanical precision but struggled with organic forms. Subdivision surfaces, borrowed from Pixar's animation workflows, allowed designers to sculpt smooth, flowing shapes that felt natural in human hands. The iPhone XS controversial curved edges, dismissed by competitors as cosmetic fluff, actually represented a manufacturing tour de force. Every curve was mathematically precise, generated from subdivision control meshes that maintained both aesthetic beauty and tooling feasibility. When Samsung attempted to copy the design using traditional NURBS modeling, their tooling costs exceeded Apple's by 300%. AEC's parametric awakening Bentley's MicroStation leveraged constrained propagation algorithms to tackle architecture's greatest challenge, coordinating massive building projects across dozens of disciplines. The Burj Khalifa project, with its 163 floors and 24,348 individual components, became a testing ground for parametric building information modeling. The breakthrough came when structural modifications automatically propagated through mechanical, electrical, and plumbing systems. A beam resize in the structural model would automatically adjust ductwork routing, electrical conduit paths, and even furniture layouts. The Burj Khalifa construction proceeded with zero major coordinate conflicts, a first in skyscraper history. Open-source disruption Blender's entry into CAD territory seemed quixotic. A free animation package challenging commercial CAD giants worth billions? The Blender Foundation's 2019 Canadian dollars tools announcement was met with industry skepticism, but by 2023, something unexpected was happening. Small design studios, previously locked out by $15,000 annual software licenses, began creating commercial products using Blender's parametric modeling tools. The disruption wasn't in features. Blender's CAD tools remained primitive compared to commercial offerings. The disruption was in accessibility. A generation of designers grew up with free tools, unburdened by licensing restrictions or corporate IT policies. Their designs, uncompromised by software limitations, began influencing mainstream CAD development. Major vendors quietly began copying Blender's user interface paradigms, proving that innovation could flow upward from open-source foundations. The AI convergence. By 2023, artificial intelligence had transformed from CAD curiosity to industrial necessity. The transformation began quietly in topology optimization labs but exploded into mainstream consciousness when Altair's Inspire AI reduced Airbus A350 wing component mass by 15% while maintaining structural integrity. Generative topologies. The concept seemed like science fiction, described performance requirements, and AI would generate optimal geometries. But Altair's neural networks, trained on millions of finite element analyses, could predict structural performance faster than traditional optimization methods. The A350 wing bracket optimization that previously required weeks of iterative design was completed in 4 hours. The implications extended beyond weight savings. Generative design produced forms that human intuition would never conceive, lattice structures that looked organic but performed with mechanical precision. Boeing 787 interior components, generated by AI topology optimization, reduced part count by 40% while improving passenger space utilization. Real-time ray tracing revolution. NVIDIA's RTX ray tracing acceleration transformed collision detection from computational bottleneck to real-time capability. Complex assemblies with thousands of components could now check for interferences in milliseconds rather than minutes. The technology's first major deployment came at Ford's Dearborn plant, where assembly line workers used RTX accelerated tablets to verify component fitment before installation. The real breakthrough came when ray tracing merged with physics simulation. Parts could be virtually dropped into assemblies, with realistic collision and gravity simulation ensuring proper fit. Manufacturing errors, previously discovered during expensive physical prototyping, were eliminated in virtual space. Cloud kernels and global design. Tesla's 24/7 global design workflow represented the ultimate expression of distributed CAD development. Design teams in Fremont handed off work to Shanghai engineers at shift change, who passed models to Berlin teams 8 hours later. The continuous design cycle, enabled by cloud-based geometry kernels, compressed traditional development timelines by 60%. The technology challenges were immense. Geometry streaming across continents required bandwidth optimization and latency compensation. Model conflicts from simultaneous editing needed real-time resolution. But the competitive advantages were overwhelming. Tesla could iterate designs faster than traditional automakers could convene meetings. The digital twin emergence. The convergence of CAD kernels with IoT sensors created an entirely new category, the digital twin. These weren't static models but living representations of physical objects, continuously updated by real-world performance data. General Electric's jet engine digital twins collected data from 5000+ sensors during flight, automatically updating CAD models to reflect actual component wear. Maintenance schedules shifted from calendar-based to condition-based, reducing unnecessary overhauls by 70% while improving safety margins. The technology's most profound impact came in design feedback loops. Future engine versions incorporated lessons learned from current engines' digital twins, creating an evolutionary design process that improved with every flight hour. By 2024, GE's latest turbofan designs had never existed in physical form before certification. They were designed, tested, and optimized entirely in digital space.